Around about 2017, 2018, we're seeing a flurry of AI applications, exactly the kind of things I've described, things like recognizing tumors and so on. And those developments alone would have been driving AI ahead. But what happens is one particular machine learning technology suddenly seems to be very, very well suited for this age of big AI. The paper that launched all this, probably the most important AI paper in the last decade, is called Attention is All You Need. It's an extremely unhelpful title, and I bet they're regretting that title. It probably seemed like a good joke at the time. All you need is a kind of AI meme. Doesn't sound very funny to you. That's because it isn't very funny. It's an insider AI joke. But anyway, this paper by these 7 people who at the time worked for Google Brain, one of the Google research labs, is the paper that introduces a particular neural network architecture called the transformer architecture. And what it's designed for is something called large language models. So I'm not going to try and explain how the transformer architecture works. It has one particular innovation, I think, and that particular innovation is what's called an attention mechanism. So we're going to describe how large language models work in a moment. But the point of the picture is simply that this is not just a big neural network. It has some structure. And it was this structure that was invented in that paper, and this diagram is taken straight out of that paper. It was these structures, the transformer architectures, that made this technology possible. Okay, so we're all busy, sort of semi-locked down and afraid to leave our homes in June 2020. And one company called OpenAI released a system, or announced a system, I should say, called GPT-3. Great technology. Their marketing company with GPT, I really think could have done with a bit more thought, to be honest with you. Doesn't roll off the tongue. But anyway, GPT-3 is a particular type of machine learning system called a large language model. And we're going to talk in more detail about what large language models do in a moment, but the key point about GPT-3 is this. As we started to see what it could do, we realized that this was a step change in capability. It was dramatically better than the systems that had gone before it. Not just a little bit better, it was dramatically better than the systems that had gone before it. And the scale of it was mind-boggling. So, in neural network terms, we talk about parameters. When neural network people talk about a parameter, what are they talking about? They're talking either about an individual neuron or one of the connections between them, roughly. And GPT-3 had 175 billion parameters. Now, this is not the same as the number of neurons in the brain, but nevertheless, it's not far off that order of magnitude. It's extremely large. But remember, it's organized into one of these transformer architectures. My point is, it's not just a big neural network. And so the scale of the neural networks in this system were enormous, completely unprecedented. And there's no point in having a big neural network unless you can train it with enough data. And actually, if you have large neural networks and not enough data, you don't get capable systems at all. They're really quite useless. So what did the training data look like? The training data for GPT-3 is something like 500 billion words. It's ordinary English text. Ordinary English text. That's how this system was trained, just by giving it ordinary English text. Where do you get that training data from? You download the whole of the World Wide Web to start with. Yeah? Literally, this is the standard practice in the field. You download the whole of the World Wide Web. You can try this at home, by the way. No, if you have a big enough disk drive, there's a program called Common Crawl. You can Google Common Crawl when you get home. They've even downloaded it all for you and put it in a nice big file ready for your archive, but you do need a big disk in order to store all that stuff. And what that means is they go to every web page, scrape all the text from it, just the ordinary text, and then they follow all the links on that web page to every other web page. And they do that exhaustively until they've absorbed the whole of the World Wide Web. So what does that mean? Every PDF document goes into that, and you scrape the text from those PDF documents. Every advertising brochure, every bit, every government regulation, every university minutes, God help us, all of it goes into that training data, okay? And the statistics, 500 billion words, it's very hard to understand the scale of that training data. It would take a person reading 1,000 words an hour more than 1,000 years in order to be able to read that. But even that doesn't really help. That's vastly, vastly more text than a human being could ever absorb in their lifetime. What this tells you, by the way, one thing that tells you is that the machine learning is much less efficient at learning than human beings are. Because for me to be able to learn, I did not have to absorb 500 billion words. Anyway, so what does it do? So this company, OpenAI, that are developing this technology. They've got $1 billion investment from Microsoft. And what is it that they're trying to do? What is this large language model? All it's doing is a very powerful autocomplete. So if I open up my smartphone and I start sending a text message to my wife and I type, "I'm going to be," my smartphone will suggest completions for me so that I can type the message quickly. And what might those completions be? They might be late or in the pub, or late and in the pub. So how is my smartphone doing that? It's doing what GPT-3 does, but on a much smaller scale. It's looked at all of the text messages that I've sent to my wife, and it's learned through a much simpler machine learning process that the likeliest next thing for me to type after "I'm going to be" is either late or in the pub, or late and in the pub. So the training data there is just the text messages that I sent to my wife. Now, crucially, what GPT-3 and its successor, ChatGPT, all they are doing is exactly the same thing. The difference is scale. The difference is scale. In order to be able to train the neural networks with all of that training data so that they can do that prediction, given this prompt, what should come next, you require extremely expensive AI supercomputers running for months. And by extremely expensive AI supercomputers, these are tens of millions of dollars for these supercomputers, and they're running for months. Just the basic electricity cost runs into millions of dollars. That raises all sorts of issues about CO2 emissions and the like that we're not going to go into there. The point is, these are extremely expensive things. One of the implications of that, by the way, no UK or US university has the capability to build one of these models from scratch. It's only big tech companies at the moment that are capable of building models on the scale of GPT-3 or ChatGPT. So GPT-3 is released, I say, in June 2020, and it suddenly becomes clear to us that what it does is a step change improvement in capability over the systems that have come before. And seeing a step change in one generation is extremely rare. But how did they get there? Well, the transformer architecture was essential. They wouldn't have been able to do that. But actually, just as important is scale. Enormous amounts of data, enormous amounts of computer power that have gone into training those networks. And actually, spurred on by this, we've entered a new age in AI. When I was a PhD student in the late 1980s, I shared a computer with a bunch of other people in my office, and it was fine. We could do state-of-the-art AI research on a desktop computer that was shared with a bunch of us. We're in a very different world. The world that we're in AI now, the world of big AI, is to take enormous data sets and throw them at enormous machine learning systems. And there's a lesson here that's called The Bitter Truth. This is from a machine learning researcher called Rich Sutton. And what Rich pointed out, and he's a very brilliant researcher, won every award in the field, he said, look, the real truth is that the big advances that we've seen in AI has come about when people have done exactly that. Just throw 10 times more data and 10 times more compute power at it. And I say it's a bitter lesson because as a scientist, that's exactly not how you would like progress to be made. Okay. So, when I was a student, I worked in a discipline called symbolic AI. And symbolic AI tries to get AI, roughly speaking, through modeling the mind, modeling the conscious mental processes that go on in our mind, the conversations that we have with ourselves in languages. We tried to capture those processes in artificial intelligence. In big AI, and so the implication there in symbolic AI is that intelligence is a problem of knowledge, that we have to give the machine sufficient knowledge about a problem in order for it to be able to solve it. In big AI, the bet is a different one. In big AI, the bet is that intelligence is a problem of data. And if we can get enough data and enough associated computer power, then that will deliver AI. So there's a very different shift in this new world of big AI. But the point about big AI is that we're into a new era in artificial intelligence where it's data-driven and compute-driven and large machine learning systems. So, why did we get excited back in June 2020? Well, remember, what GPT-3 was intended to do, what it's trained to do, is that prompt completion task. And it's been trained on everything on the World Wide Web. So you can give it a prompt like a one-paragraph summary of the life and achievements of Winston Churchill, and it's read enough one-paragraph summaries of the life and achievements of Winston Churchill that it will come back with a very plausible one. Yeah, and it's extremely good at generating realistic-sounding text in that way. But this is why we got surprised in AI. This is from a common sense reasoning task that was devised for artificial intelligence in the 1990s. And until 3 years ago, until June 2020, there was no AI system that existed in the world that you could apply this test to. It was just literally impossible. There was nothing there. And that changed overnight. Okay? So what does this test look like? Well, the test is a bunch of questions, and they are questions not for mathematical reasoning or logical reasoning or problems in physics. They're common sense reasoning tasks. And if we ever have AI that delivers at scale on really large systems, then it surely would be able to tackle problems like this. So, what will the questions look like? The human asks the question, if Tom is 3 inches taller than Dick, and Dick is 2 inches taller than Harry, then how much taller is Tom than Harry? The ones in green are the ones it gets right, the ones in red are the ones it gets wrong. And it gets that one right, 5 inches taller than Harry. But we didn't train it to be able to answer that question, so where on earth did that come from? Where did that capability, that simple capability to be able to do that, where did it come from? The next question, can Tom be taller than himself? This is understanding of the concept of taller than, that the concept of taller than is irreflexive. You can't be taller, a thing cannot be taller than itself. Now, again, it gets the answer right, but we didn't train it on that. We didn't train the system to be good at answering questions about what taller than means. And by the way, 20 years ago, that's exactly what people did in AI, right? So where did that capability come from? Can a sister be taller than her brother? Yes, a system can be taller than a brother. Can two siblings each be taller than the other? And it gets this one wrong. And actually, I have puzzled. Is there any way that its answer could be correct? And it's just getting it correct in a way that I don't understand. But I haven't yet figured out any way that answer could be correct. Right? So why it gets that one wrong, I don't know. Then this one I'm also surprised at. On a map, which compass direction is usually left? And it thinks north is usually to the left. I don't know if there's any countries in the world that conventionally have north to the left, but I don't think so. Yeah. Can fish run? No, it understands that fish cannot run. If a door is locked, what must you do first before opening it? You must first unlock it before opening. And then finally, and very weirdly, it gets this one wrong. Which was invented first, cars, ships, or planes? And it thinks cars were invented first. No idea what's going on there. Now, my point is that this system was built to be able to complete from a prompt. And it's no surprise that it would be able to generate a good one-paragraph summary of the life and achievements of Winston Churchill, because it will have seen all that in the training data. But where does the understanding of taller than come from? And there are a million other examples like this. Since June 2020, the AI community has just gone nuts exploring the possibilities of these systems and trying to understand why they can do these things when that's not what we trained them to do.